Hello, welcome to the course SJPHY3BO3 Electrodynamics 1. The contents of this course is taken from Introduction to Electrodynamics by David J. Griffiths. We'll continue to discuss topics from Chapter 5 Magnetostatics. In the last class, we have seen how to calculate the magnetic field associated with a given current configuration using Biot-Savart law. Today, let's try to calculate what are the curl and divergence of the magnetostatic field. Coming to the curl first, let's take a specific case of a current carrying straight wire, because in the last class we have seen how to calculate the magnetic field associated with this configuration using Biot-Savart law. And for this special case, we will determine what is the curl, and later on we will develop a more generic framework for any given current configuration. Now, in the case of a current carrying wire, now assume that you have a wire pointing towards you out of the page. So this is denoted by this dot here, and as we know, magnetic field lines curl around this given wire. So from the very geometry itself, we can notice that there is a non-zero curl involved here. So let's choose one of the loops, for example the last loop, and assume that it is at a distance s from the wire. So the magnetic field using Biot-Savart law we have calculated as mu naught I divided by 2 pi s. Now for this loop, let's calculate what is the line integral of the magnetic field. So closed line integral B dot dl. B is nothing but mu naught I by 2 pi s. For a given s, this is a constant. I can take it outside the integral. This is mu naught I divided by 2 pi s line integral dl. Now what is the line integral along this closed loop? This is nothing but the perimeter of this loop, right? So for a radius of s, perimeter is 2 pi s. So 2 pi s cancel, you have mu naught I. So for this closed loop, the line integral of magnetic field is nothing but mu naught I. Suppose we have a bundle of straight wires. Okay, then you have a circular loop here, and if you calculate the line integral of magnetic field along this loop, then each of the wires which passes through this loop contributes a current mu naught I, and the wires which are outside of the loops do not contribute anything. So I can write a line integral of B dot dl is nothing but mu naught into I enclosed, where I enclosed is the total current enclosed by this loop. So in this particular case, I enclosed is nothing but I4 plus I3 plus I1. Since I5 and I2 are outside of the loop, they do not contribute to this integral. Or in terms of the volume current density J, I can write I enclosed equal to integral J dot dA. So mu naught I enclosed is nothing but mu naught into surface integral J dot dA. The line integral on the left hand side I can convert into surface integral using Stokes' theorem. So the left hand side becomes integral curl of B dot dA equal to mu naught integral J dot dA. I have similar surface integrals on both sides, which means I can equate the term inside. When I do that, I get curl of B equal to mu naught J. So this is the value of curl of magnetostatic field associated with a current carrying straight wire. Later on we will see that for any given current configuration, this expression is valid. Moving on to divergence of magnetic field, assume that you have a three-dimensional region filled with volume current density J, and at a reference point which is at a distance r from this given volume, what is the magnetic field? We know how to determine the strength of the magnetic field using Biot-Savart law. So which says that B of r equal to mu naught over 4 pi integral J cross r cap by r square d tau prime. As I said in the previous class, the source element is characterized by r prime vector, and the reference point is characterized by the r vector, and the distance between these two is characterized by the displacement r vector. So let's be thorough with the notations involved here. Since we are calculating the magnetic field at a reference point where the position vector is given by the r vector, we can say that magnetic field is always a function of r or x, y, z. Source element is always associated with r prime. Since the source of the magnetic field is the current density, so I can say current density J is a function of r prime or x prime, y prime, z prime. What about the displacement? This is r minus r prime. So I can write it as x minus x prime x cap plus y minus y prime y cap plus z minus z prime z cap. So this is a function of both r and. What about the volume element here? Once again, this is associated with the source, so it is a function of r prime. So in Cartesian coordinate system, I can write d tau prime is dx prime, dy prime, dz prime. And the del operator, as always, this is a function of r, so I can write it as dou by dou x x cap plus dou by dou y y cap plus dou by dou z z cap. Sorry for the typo here. This should be dou y, this should be dou z. If you look at this expression, the integration is done over the volume element, which is a function of r prime. So I can say the integration is over the primed coordinates. On the other hand, if you take divergence and curl of B, both are functions of r, the unprimed coordinates. So I can say divergence and curl of B are with respect to the unprimed coordinates. So once again, the integration is with respect to the prime coordinates, and divergence and curl are calculated with respect to the unprimed coordinates. Let's calculate the divergence of magnetic field. From this expression, I can write divergence of B equal to divergence of this expression. I can interchange between the integral and the differential. So I can write mu naught over 4 pi integral divergence of j cross r cap by r square d tau prime. Invoking product rule from the first chapter, I can write a divergence of A cross B equal to B dot curl of A minus A dot curl of B. So using this, I can write a divergence of J cross R cap by R square equal to R cap by R square into curl of J minus J dot del cross R cap by R square. So let's calculate the value of curl of J and curl of R cap by R square. Curl of J is 0 because as I said, the del operator depends on the prime coordinates, whereas J depends entirely on the unprime coordinates. So this gives you 0. What about curl of R cap divided by R square? R cap by R square you can also write as R to the power minus 2 into R cap. So in general, if you take the function r to the power n into r cap, let's find out the curl of this function. So invoking the polar coordinate system, you can write this in terms of the polar coordinates as 1 over r square dou by dou r square r to the power n. You don't have to worry about the theta and phi components because those two are absent here. So this is nothing but 1 over r square dou by dou r to the power n plus 2, whose differential is n plus 2 into r to the power n plus 1. So when you divide this with r square, you get n plus 2 into r to the power n minus 1. Now if you compare this with our given function r to the power minus 2 into r cap, the value of n is equal to minus 2. If you substitute for n in this expression, for n equal to minus 2 plus 2 will give you 0. So the value of curl of r cap divided by r square equal to 0. So in this expression, curl of j equal to 0, curl of r cap by r square equal to 0. So when you substitute in this expression, you get divergence of B equal to 0. So this is a generic expression for any given current configuration. The value of divergence of the magnetostatic field is always 0. What about curl of B? Since we have a general expression for magnetic field here, I can find out the general expression for curl of B using that equation. So from equation for B, I can write curl of B equal to mu naught divided by 4 pi integral curl of j cross r cap by r square d tau prime. Now we need to calculate the value of the term inside. Okay. Once again, invoking the product rule from chapter 1, I can write curl of A cross B equal to B dot del into A minus A dot del into B plus A into del dot B minus B into del dot A. So using the product rule, I can expand curl of J cross R cap by R square as R cap by R square dot del into J minus J dot del into R cap by R square plus J into del dot R cap by R square minus R cap by R square del dot J. Now the value of del dot J equal to 0 because del depends on the unprime coordinates and J depends entirely on the prime coordinates. Since A dot B is same as B dot A, using the same argument I can also say that J dot del is also 0. Now R cap by R square dot del, and this is 0. You can do it for yourself or you can refer to chapter 1. The proof for this particular expression is given. So these three terms get cancelled. Essentially you are left with only one term, which is J into del dot R cap by R square. What's the value of the term inside the bracket? Once again, you can refer to chapter 1 on vector analysis. This is a very standard result. The proof for this is given in chapter 1. So the value of del dot R cap by R square is 4 pi delta cube R, where delta cube R is nothing but the Dirac delta function. Hope you are already familiar with the Dirac delta function. If you take delta function in one dimension, delta x is defined as its value is 0 if x is not equal to 0, and at x equal to 0 its value equal to 1. Basically the value of a delta function is 0 everywhere except at the point x equal to 0. So even though in this graph there is a certain thickness to this function, in reality this should be a straight line at the point x equal to 0 and everywhere else it should be 0. And because of the particular nature of this function, if you integrate it from minus infinity to plus infinity, the value is going to be 1, because only at this point the value of the function is 1, everywhere else it is 0. So when you do the total integration, the final sum should amount to unity. That's about a one-dimensional Dirac delta function. Three-dimensional Dirac delta function is just an extension of this. So in the case of delta cube R, when R equal to 0, the value of the function is 1. Everywhere else, the value of the delta function is 0. When R equal to 0, R is defined as R minus R prime. So when R equal to 0, I can write R equal to R prime. Now let's put this back into our expression for a curl of B. So if you do that, you get curl of B equal to mu naught over 4 pi integral j of r prime 4 pi delta cube. Instead of r, I can write r minus r prime d tau prime. So we know that when r equal to r prime, the value of delta cube equal to 1. Everywhere else it is 0. Okay. So there is no point in doing this integration now, because essentially we need to calculate the value of this integral at a single point. Okay. So you can neglect this integration and straight away go to this point r equal to r prime and calculate the value of this function. So at r equal to r prime, what is the value? Mu naught over 4 pi j of, instead of r prime I can write r multiplied by 4 pi, then value of this is equal to 1. So 4 pi cancel, I have mu naught into j. So curl of B equal to mu naught j. This is the same result we have got in the specific case of a long straight current carrying wire. So for any given configuration, this expression is valid. And this is known as Ampere's law in differential form. Let's quickly calculate what is the integral form of this equation. Since I have this equation, what I can do is I can do the surface integral on either side. So surface integral of curl of B equal to surface integral of mu naught j. This is what I have written here. Since mu naught is a constant, I can take it outside the integral and write mu naught into surface integral j dot dA. Now the surface integral on left hand side I can convert into line integral using Stokes' theorem. So the left hand side becomes closed line integral B dot dl equal to mu naught into integral j dot dA. Since integral j dot dA is nothing but the total current enclosed by the Amperian loop, I can write integral B dot dl equal to mu naught I enclosed. So this is known as Ampere's law in differential form. So if you want to quickly compare between electrostatics and magnetostatics, in electrostatics, to find out the value of the electrostatics field, you have the Coulomb's law. Similarly, in magnetostatics, we have the Biot-Savart law. In both cases, we have seen that as the distance from the source increases, both electric field and magnetic field decrease. In electrostatic field, you had the Gauss law. Similarly, we also have the Ampere's law in magnetostatics. Now you have two choices to calculate the magnetostatic field, either using the Biot-Savart law or using the Ampere's law. Let's quickly test the utility of Ampere's law. In the last class, we have found out the magnetic field at a distance s from a long straight wire carrying a steady current I using the Biot-Savart law. Now let's do the same problem using Ampere's law. Okay, so I have a straight long wire carrying uniform current I. At a distance s, I want to calculate what is the strength of the magnetic field. So what do we do? So just assume an Amperian loop. It need not be circular, it could be of any shape, doesn't matter. Just for convenience, we use the circular Amperian loop here. So I have a circular Amperian loop of radius s enclosing the wire. Now I can write Ampere's law in the integral form. Sorry for the typo here, this should have been integral form. So the Ampere's law in integral form says integral B dot dl equal to mu naught I enclosed. From the nature of the magnetic field, I know that around, if you take a circular loop around the wire, along this loop, the value of the magnetic field is a constant. So I can take magnetic field outside the integral and write B into integral dA. Also, the direction of the magnetic field and the direction of the circular loop both are same. Since I am talking about two parallel vectors here, I can get rid of the dot product and use the normal product. Okay. Now, Integral of dl is nothing but the circumference of the circular loop, which is 2 pi s. So the left hand side is b into 2 pi s, which is nothing but mu naught into I enclosed. Now what is the total current enclosed by this ambient loop? This is nothing but the steady current I. So right hand side becomes mu naught I. So b into 2 pi s equal to mu naught I, or b equal to mu naught I divided by 2 pi s. So I hope the difference between Ampere's law and Biot-Savart law is pretty clear here. If you recollect the same exercise we have done in the previous class, it took us almost one page to arrive at this result using Biot-Savart law. On the other hand, using Ampere's law with 2 steps, we got the same result. So this is the major advantage of Ampere's law over Biot-Savart law. It yields you the result much more quickly compared to Biot-Savart law. But the issue with Ampere's law is you can apply this only in specific condition. So the condition is that the symmetry of the problem should allow you to take the magnetic field outside this integral. Only then you can apply Ampere's law and get the result quickly. So the scope of Ampere's law is very limited. You can apply this only in special condition. On the other hand, Biot-Savart law you can apply in any condition. Whatever is the current configuration, you can apply the Biot-Savart law. The only downside is this is more tedious. So the scope of Biot-Savart law is higher, but it is more tedious, whereas the scope of Ampere's law is lower, but this is much more simple. Now, which are the conditions in which I can apply Ampere's law and get the result? So, one condition we have discussed already in the case of long straight wire. In the next class, we will also discuss 2 more cases. One is a solenoid, second is a circular solenoid known as toroid. In both the cases, we will see how to compute the magnetic field very easily using the Ampere's law. That's for today. Thank you.